and the mass of atoms in particular. And you just got through learning that because the nucleus contains all the mass and that each nucleus contains different numbers of protons and neutrons, bottom line is that every atom is going to have a different mass. And that's going to cause some problems in the sense that mass is one of the most fundamental properties that we measure. And yet, if each atom has a different mass, we need a way to cope with that. Well, the idea here was to define a new unit, an atomic mass unit, to measure very, very small masses you saw on the previous talk or in class or in a table, the very, very tiny masses that we're dealing with. So it made sense to define a new mass unit for dealing with these very small things. The AMU, atomic mass unit, is that unit, and it's based on the mass of one particular element. We chose carbon for convenience, for a variety of historical reasons, but in whatever it is, the point is that we use that element, and 1 AMU is exactly 1/12 the mass of one carbon-12 atom. If you think about that, it makes sense. Carbon, atomic number 6, carbon-12 would have 6 protons and 6 neutrons. And if we divide that by 12, we'll have one essentially nucleon. Remember that each of those nucleons has an atomic mass of 1 to 2 significant figures, and away we go. This AMU then is the mass of unit we use to measure the mass of atoms. If you look at the periodic table, though, you'll see that the mass that is listed there is not an integer. The mass number of the isotope is always an integer. There's always a whole number of protons and neutrons in the nucleus, and so something's going on here because the mass that is shown on the periodic table is not an integer, but rather a decimal, suggesting fractional numbers of protons, neutrons, or whatever. So we need to deal kind of with that. The idea is, of course, that there are varying isotopes for all elements, differing numbers of neutrons in that nucleus. And so there can be different numbers of isotopes and different masses for those isotopes. The problem lies in the fact that almost always one isotope is very abundant and the others are much less abundant. And what this means is in order to us to calculate the average atomic mass, we're going to have to weight the isotopes by their abundance. You won't have to do this. It's essentially just an explanation for why, on the one hand, we talk about the mass of atoms as being essentially a whole number, an integer, whereas in the periodic table, where every time we want to get the average atomic mass, we'll just read the number right off the table and it will be a decimal number. And this example shows what happens when you take 3 different isotopes. This happens to be nitrogen, that have varying abundance. Notice that the 82 plus the 14 plus the 4 would add up to 100%. And then weight the mass by that abundance, we end up indeed with an average value here, and that is the number that is shown on the periodic table. Generally, the isotopes are all well mixed together in a particular sample of any given size, and so that allows us to use this average atomic mass as a representation for the element. The final problem has to do with the fact that since every atom, every element is going to have a different average atomic mass, we're going to have to find a way to translate that into some kind of thing that we can measure in our laboratory, a mass conveniently rendered in grams. The mole is probably the most fundamental concept in chemistry, in as much as it is the translator between the average atomic mass in AMU and the mass in grams. If you think about it, once we defined the element that we're going to use for our standard, only one number of particles would make that average atomic mass in AMU equal to the atomic mass in grams, and that, ladies and gentlemen, is the mole. The mole is a number like a dozen, meaning that all it is the number of particles that it would take in order for the mass in AMU to be equal to the mass in grams. It happens to have the numerical value of 6.022 times 10 to the 23rd, a lot of particles because the atom is very small. It's called Avogadro's number. And at the bottom there, the statement that more or less completes the loop. If you took 6.022 times 10 to the 23rd carbon 12 atoms, you would end up with a mass of exactly 12 grams. And so now we have the number that allows us to work effortlessly between a easily measured quantity, mass, and the actual number of particles. The key here is that because chemical reactions occur on a particle-to-particle basis, we have to know how many particles we have in order to figure out what we're going to get as an outcome. Mass, of course, is the easiest thing to measure, and it is the mole then that allows us to go back and forth between mass, an easily measured quantity, and moles, the number of particles. But just like we often speak in dozens of donuts, we sometimes don't have to know exactly how many individual donuts we have. It's enough for us to know we have 12 dozen donuts or 6 dozen donuts. Likewise, we'll often just use the mole as our unit because it's easy to transform moles into mass should the need arise. It will arise quite often in many cases, but you also will have a calculator on Wolfram Alpha, I believe, that does this thing for you immediately, and so it's important really for you just to understand how it works. As the guy says there, we're now set to go. We have a new then quantity that we'll use all the time, the molar mass, and I'm going to take just a second here and do a little side trip. Often this is shown on Wolfram Alpha and in Wikipedia and other resources as a molecular weight or a formula weight. Weight and mass are different things. Formula weight and molecular weight are older terms that have unfortunately carried over to the modern day. You'll oftentimes see written on bottles of chemicals FW, formula weight, and then a number. This is all the same quantity. It is molar mass, and molar mass is the way that I refer to it because it is the mass of 1 mole of substance rendered in grams. So the periodic table then becomes our resource for looking up that molar mass. You in fact can just enter the compound name or the element name into Wolfram Alpha or Wikipedia, and you would be shown in an early screen what that molar mass, formula weight, molecular weight is, and away we go. It makes perfect sense that not only can we use the number off the periodic table to get the molar mass of an element, but that we can build up molar masses to get compounds. Here an example, if you look at gold on the periodic table or just type it into one of your resources, we have a molar mass of 197, a formula mass, 197 AMU. This would be the mass of 1 atom of gold. And the molar mass is exactly the same number, and that's the key concept because the mole translates our mass directly into moles and back and forth. Sodium chloride here as another example. The mass of sodium 22.0, 35.5 for chloride. All we got to do is add them up. Notice that we can have a mass in AMU if we're talking about 1 formula unit of sodium chloride, but we're far more likely to be dealing with a large amount, and hence the idea of a molar mass and 58.5 grams being the molar mass of that compound makes a lot of sense. If you type into, again, any of your resources, the formula for something, a compound or an element, or you type in the words, silver nitrate or whatever, one of the early things that comes back at you is the molar mass or formula weight. And so as the guy says, now again, we can go from mass to moles, from moles to particles, from particles to moles effortlessly by using the 2 conversion factors, right? Molar mass and Avogadro's number, depending on where we want to go. Again, as I said before, chemical reactions take place on a particle-to-particle basis, but we measure mass, and so we have to convert, and moles then is the thing in terms of the device getting back and forth. Just do a couple of quick problems just to show you. Again, these calculations can be routinely done in your resources. Wolfram Alpha, in particular, will convert a mass into moles and probably into particles as well if we need to. Let's just say we're going to convert 2.6 moles of aluminum into mass terms. All we would have to do, of course, is configure our conversion factor to convert moles, 1 mole Al, into mass grams. And all I have to do is grab my trusty periodic table, find the molar mass of aluminum. It is 27.0 grams, rounded to 3 significant figures, and significant figures do apply here. Then all I have to do is do that arithmetic, grab my trusty calculator, 2.6 times 27, I get 70.2 grams. I check and see I have 2 significant figures here, 3 significant figures there, so I only get 2 significant figures in my answer. But since that 0 would be significant, I would put that decimal point there, and away we go. We can go from atoms to moles by using Avogadro's number, 3.45 times 10 to the 21 atoms. Notice that 1 mole of any substance is the same number of particles, so it doesn't matter in this problem that we're talking about potassium. 1 mole, 6.02 times 10 to the 23rd atoms. Notice I'm using my shorthand E notation there. All I got to do here is divide by Avogadro's number, and I get 0.0057 mole. Notice I've got 3 significant figures here, 3 significant figures here, so I can actually add another significant figure there, and there's my answer. Mass to moles, moles to mass. We're going to do it all the time, and we'll continue to practice in the next video.